All right, how's it going, everybody? Give me a couple seconds to get um, everything situated. This is I'm gonna something I've been wanting to do for a while, but I got the page going and everything about probably a month ago, and I don't think I'm really on here, am I? I don't think I'm really on here, am I? If this is really working right now, bear with me for 1 second, please. Okay, checking 1, 2, 3. Checking 1, 2, 3. Okay, checking 1, 2, 3. Check. Checking 1, 2, 3. Okay, checking 1, 2, 3. Okay, check. So it looks like there's about a 30-second delay, but it looks like I'm running. Checking 1, 2, 3. I'm also hearing an echo. Okay, checking 1, 2, 3. Okay, check. So it looks like there's about a 30-second delay, but it looks like I'm running. Checking 1, 2, 3. I'm also hearing an echo. Okay, check. So it looks like there's about a 30-second delay, but it looks like I'm running. Checking 1, 2, 3. So here you an echo. Okay, check. So it looks like there's about a 30-second delay, but it looks like I'm running. Checking 1, 2, 3. So here you an echo. Okay, check. So it looks like there's about a 30-second delay, but it looks like I'm running. Checking 1, 2, 3. So here you an echo. Okay, I want to try something else out real quick here. Hey, this is my first time doing this. I know there's nobody watching, so bear with me for 1 second, please. Just trying to get rid of the echo. I think I have it figured out. Okay, we're almost 10 minutes into it. Let's get this going. Okay, so what we're going to do is a little project I've been wanting to do for a while now, but as you can tell by the previous 9 minutes or so, I'm not that you know the word I'm trying to say. I guess I'm not as clever as I used to be with these computers and stuff, so I'm figuring everything out on the fly. So I put up this page maybe a month, 6 weeks ago, and it's just barely to today where I've been able to get a stream going. So what I'm going to attempt to do with this project is teach myself math, and if I can keep going, I'm going to start here with algebra, and I'm going to go all the way up to wherever. I'd like to be able to go to some type of postgraduate level of math, but we'll see. I encourage Anybody to watch, anybody to backseat, basically help me out with problems if you're watching. It looks like there's about a 30-second delay on from what I'm doing to what you see on the stream. So obviously, um, that might be an issue. I don't know down the road. But what I'd like to do is if you're watching and you are more than welcome to help out, give me your input. If it pertains to the topic we're on, then if you have any questions, you know, the more we work on this, the better we get. The only thing I ask is if they're not, if it doesn't pertain, like today we're starting at the beginning, so we're doing real numbers. If you come in here with a question about, uh, limits or something from calculus, I'm not going to be able to answer it. But yeah, and if, there's actually people in the chat, you guys can ask each other questions too. I don't necessarily need to be the one that is answering them. Anyway, let's get this going. Let's not waste any more time. So we're going to start at the bottom. Well, this might not be the technical bottom, but hey, come on. I know what 2 plus 2 is. I know, you know, I know my basic math. So we'll just start, high school level or junior high, something you would learn, past the basics. So this is a book I got from online. I'm going to take this from. I don't. It, it was on a website that had free textbooks. I don't know if they're free because they have them, with some not so honest means, or if they have the ability to give these textbooks out for free or not. I'm not sure, so I'm not going to say what the name of the math book is just because um, I don't want to get myself in trouble or in the stream since I don't know how that kind of stuff works. I'll be on the safe side, or at least lean towards the safe side, just in case I was doing something I shouldn't have been doing that I didn't know I shouldn't have been doing. But the website seemed legit, so it doesn't appear to be a textbook that is currently used, or at least not the edition. You know how you can be on the 15th edition of the textbook. That scam to get you to buy more books. Anyway, I've talked long enough, I think, with nothing to say really. And I think I've repeated myself a couple times. But anyway, chapter 1 in this book is real numbers and their operations. Sorry, I think I just burped into the microphone. I got to be cautious of those things. You can hear every little thing I'm doing. I'm probably making too much background noise. I apologize. And we're almost 15 minutes into this and I haven't started. So let's get going. Chapter 1, real numbers and their operations. Another thing I wanted to say too is I'm going to be working at my own pace. So if you are watching this and you want to learn, uh, I'm not going to go slow. So there's going to be some parts of these where I really get it and I'm going to breeze through it, and there's going to be some parts where I struggle and it's going to take me a while. If you're using this to learn and I go too fast, the only thing I can recommend then, hey, is if you're not watching live, is you rewind, or you at least look at other sources for the topic. And if you're watching live, ask questions. I'm not going to not answer your questions just because it's going to hold me back. That wouldn't be fair to you. So here we go. Once again, chapter 1, real numbers and their operations. So we're going to do real numbers in the number lines. Our objectives are to construct a number line and graph points on it. Use a number line to determine the order of real numbers. Determine the opposite of a real number. Uh, the opposite of a real number, wouldn't that be a fake number? Haha. Determine the absolute value of a real number. Anyway, definitions. A set is a collection of objects typically grouped with braces. So what I have here is this grid paper so I can draw and you guys can see stuff. So a set is a collection of objects typically grouped within braces. So we're looking at that. So a set is a collection of objects typically grouped within braces, where each object is called an element. So I would imagine whatever's inside these braces, that is the element. For example, red. Okay, here we go. So here's the example. We have red. Okay, this is not the easiest thing to write on, so it's going to be sloppy, but you get it. So we got red, green, blue is a set of colors. A subset is a set consisting of elements that belong to a given set. For example, this, whoops, that's a horrible bracket. We'll just write G for green, B for blue. That is a subset of the color set above. So this is a set. This is a subset because it contains green and blue, which are part of this bigger set above. A set with no elements is called an empty set. So if we just had this, that's an empty set. Or it can be written as this. Well, in studying mathematics, we focus on special sets of numbers. The set of natural or counting numbers is denoted as n. So n equals I wonder if I can do this. Let me try something. I was hoping I could copy and paste on this. Doesn't look like I can. Oh, I can. Here we go. Let's see. Paste from clipboard. Multiply dot. Okay, let's try this again. Sorry guys, it's slow, but this is learning for me too. Yeah, I'll try and figure this out later. Anyway, so the n here, that denotes the set of natural or counting numbers. And it is combined with 0. So we end up with a set with the brackets starting at 0, 1, 2, Now, I believe there's a rule for the minimum amount you can put in here before you put the dots, but I'm not quite sure. But anyway. Okay, I don't want these. How do we turn this off? Okay. Oh, okay. That's probably better than my writing, but you know what? We'll keep that on there. And let's change this back to black. Okay. At this pace, we're going to be on just this one chapter for the next 2.5 weeks. Anyway, so set of whole numbers. I'm going to rewrite this because I have a feeling we're going to break this down in a second into a subset. Dot, dot, dot. So here is our set of whole numbers. So the three periods are called the ellipses and indicates that the numbers continue without bound. So yes, this just shows you that this goes on for infinity. The set of whole numbers denoted W is the set of natural numbers combined with 0. Okay, so what this is already a subset then. Because we started with the set N, and that was the set of natural or counting numbers combined with 0. So then whole numbers are a subset. Why does it do that? The set of integers, okay, oh, and this is denoted as W. Then the set of integers, which is denoted as Z. Wish this would stop disappearing on me. It consists of both positive and negative whole numbers as well as 0. So that would be the brackets. There's got to be a... Oh my gosh. And that would be coming in with the dots. Why doesn't this... That'd be -3, comma, -2. Why is this not working? Let me clear the page. Oh, now it works. Okay. Just mean might mean there's too much stuff on the page. Unfortunately, that means I can't scroll back to show you guys. So we're gonna have to figure something out. And then 2, and then dot, dot, dot. You get the point. And this is denoted with the letter Z. So these are all positive and negative whole numbers as well as 0. So what they want you to notice is the set of natural and whole numbers are both subsets of the set of integers. Okay, so the set of integers is the big mothership. And then whole numbers, which were 0. So from here up is your whole number subset. And then your natural or counting numbers. And then rational numbers we have, which are denoted by the letter Q. Rational numbers are defined as any number of the form A times B, where A and B are integers and B is not equal to 0. So B is non-zero. Decimals that repeat or terminate are rational. So for example, if we have 0.7, which equals 7 over 10, or we have 0.3 with a line over it, which is equal to 0.333 dot dot dot, and that equals also 1/3. The set of integers is a subset of the set of rational numbers because every integer can be expressed as a ratio of the integer and 1. In other words, any integer can be written over 1 and can be considered a rational number. For example, 5 equals 5 over 1. Irrational numbers are defined as any number that cannot be written as a ratio of two integers. Non-terminating decimals that do not repeat are irrational. For example, pi is irrational. Pi equals 3.1415 dot dot dot, and the square root of 2 equals 1.41421. And these don't repeat, so they're irrational. And you're going to start seeing this stuff a lot in the future. Oh, well, drawing a circle erases that instead of, point to. Is there an undo on here? I don't see an undo. Okay. The set of real numbers denoted R is defined as a set of all rational numbers combined with the set of all irrational numbers. The set of real numbers, which is denoted R, is defined as the set of all rational numbers combined with the set of all irrational numbers. So real numbers are going to cover everything. So therefore, all the numbers defined so far are subsets of the set of real numbers. So in summary, they have a picture that looks like this. So we have real numbers. And then we're going to put so then you have irrational on this side. Which are your non-repeating decimals. And then on this side you have rational. And do we remember what rational numbers are? In case we don't, we'll go back and look. So rational numbers are defined as any number in the form of a times b, where a and b are integers and b is non-zero. Decimals that repeat or terminate are rational. So rational is basically every number that's not irrational. And then a subset is integers. And integers remember, integers are both negative and positive whole numbers as well as zero. And then we have our whole numbers, which are 0, 1, 2, 3, 4, 5, etc. And then we have, let's put that down here. And then we have natural, which is almost the same as whole, except it doesn't include 0. So it just goes 1, 2, 3, and we go from there. So real numbers is the big mama. And then we have subsets under real numbers of rational and irrational. On the irrational side, that's it. On the rational side, then we have a subset of integers, whole, and natural. So on the number line, a real number line, or simply a number line, it allows us to visually display real numbers by associating them with unique points on the line. The real number associated with a point is called a coordinate. A point on the real number line that is associated with a coordinate is called a graph. To construct a number line, draw a horizontal line with arrows on both ends to indicate that it continues without bound. Next, choose any point to represent the number 0. This point is called the origin. So we draw a straight line. Whoops. So here is 0. This will be our origin. And then you want to mark off consistent lengths on both sides. Now I know there's a way to do a number line automatically on this, but I don't know how. I'm also learning this program as I go. So there's that. I should probably watch a tutorial. Anyway, so the number line, you would mark off, there's one, there's another one. Let's just pretend these are all exactly spaced. So then that's 1, 2, 3, 4, and then it goes the other way. -1, -2, -3, -4. Now, the scale does not always need to be 1 unit. In the first number line, each tick represents. So this one represents 1 unit. I could also do it where instead of being 1 unit, 2, 4. So each tick represents 2, space of 2. So as long as the hash marks are equally spaced, they can represent anything. So I could break this down into quarters. So this could represent 1/4. That means the next one would be 1/2. That means this one would be 3/4. This one would be 1, etc. So there's a bunch of ways to break it down. Now, if you want to graph this, Let's go back to equal this being 1, 2, 3, 4, dot, 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 negative 1, negative 2, negative 3, negative 4. Now to graph this, we're going to put dots. So there's 1. And of course, that makes the circle. Anyway, pretend our line is still there. I also know there's a way to make a graph box in here, and I don't remember how. I should have probably reviewed this program real quick before I jumped back into it. Oh, I think you have to do it with the math pen. There's 2 pens you can use on here. One is the math pen, which maybe I should be using more, where I draw the stuff out and then it see it guesses, and let's say that's what I was trying to draw, then I go like that. Oops. See, and now I have the box drawn out. So now we're going to do the first example. Hey, we actually get to a problem. So what they want us to do is graph on the number line with a scale where each tick represents 1/3 of a 1/3 units. And we want to graph the set of, I'll draw the set up here, -1, does that say -13? No. The -1/3 0 and 5/3 okay, so we're going to draw our number line. Remember, these are units of 1/3. So we'll have a 0, we need 1, 2, 3, 4, 5, 6, 7, 8. We want about 8 lines. So 1, 2, 3. So all these lines represent 1/3. On this side it'll be, so 1/3, 2/3. This would be 1, 1 and 1/3, 1 and 2/3. This would be 2. This would be -1. This would be -2. And then just so you get an idea, this would be 1/3, 2/3. Obviously 3/3 is 1, that's 3/3. This is 4/3, or you could write it as 1 and 1/3. Whatever you choose, but since we have 5/3 up here, let's keep it consistent. So 5/3. So you would draw the circle here for 5/3. It's better not make it disappear. You want to fill these dots in, but I can't on this, otherwise it'll erase. There's 0, -1/3 is right here. So we're going to graph here, and then we'd graph here. So these are our points. When comparing real numbers on the number line, the larger number will always lie to the right of the smaller one. So these number lines are always going to go from low to high. So that if you go this way, the numbers get smaller. If you go this way, the numbers get bigger. Which it seems like it's been pretty self-explanatory on what we've seen so far. When comparing real numbers, okay, it is clear that 15 is greater than 5, but it might not be so clear that -1 is greater than -5 until we graph each number on a number line, which is common. I see this a lot. Is people have a hard time grasping the fact that -5, or even we'll go -500, is smaller than -1. And remember, if you go back on the number graph, in fact, let's do this. We'll make 0 over here. The next hash would be -1, -2, right? Until somewhere over here you have -500. And remember, this direction is smaller. This direction, the numbers get bigger. This right here is a great Mitch Hedberg joke. What is a B, but just a scrunched up 13? So now we're going to go into some symbols. These symbols, everybody should be familiar with them. This is equal to, not equal to, and approximately equal to. So obviously you'd have 5 is equal to 5. Or you could have 5 over 5 is equal to 1. Two plus 2 does not equal 5. And then with pi is approximately 3.14. And we can say approximately because we know pi keeps going and going and going. So that's not quite it. Pretty basic stuff right there. Other symbols. We have less than, greater than, less than or equal to, greater than or equal to. So these symbols allow us to compare two numbers. So we can say -120 is less than -10. So I remember when I was a kid, we always learned this as the alligators eating the bigger number. So you have 2 is less than 10. 10 is less than 12. 5 is greater than 3. 10 is greater than 5. So the mouth always wants to eat the bigger meal. And then these, less than or equal to, I mean, you could say -10 is less than or equal to -10. That is correct because it's equal to it. A lot of times that you're going to see this in, you'll have x is less than or equal to 5. And then you'll have some where you have to solve for x. So example number 2, we're going to fill in the blank with a less than, an equals, or a greater than sign. So we have -2 blank -12. So -2 is bigger than -12, so it's greater than. Let's erase that so nobody gets confused. And to prove this, you can use the number line, and you would see, since we're using negative numbers, let's put 0 over here. There's 2, 4, 6, 8, 10. So here's -12. Remember, this way is small. This way is big. So 2 is to the right of -2 is to the right of -12. That means -2 is greater than -12. And then if you had to graph them, you could fill in your dots. This program makes it a race. There's got to be a better way. We'll figure that out soon. So the opposite of any real number, a, is -a. So the opposite of a is -a. So what that's saying is, let's replace a with a number. So we could say 5. So the opposite of 5 would be -5. Pretty simple. If you had to graph that on the number line, you could say here's 0, here's a, here's -a. They're opposites of each other. So for example, we say the opposite of 10 is -10. Now consider the opposite of a negative number. Given the integer -7, the integer the same distance from the origin and with the opposite sign is 7. So the opposite of -a is a, or -7 in this case would be 7. And how you can find it on the number line, it's going to be the same amount of spaces. So if with 5, for instance, 5 would be 5, the distance of 5 over 1, 2, I don't think that's 5, but 2, 3, 4, 3. So there's 5. So you got 1, 2, 3, 4, 5. They're equal distance apart from 0. So that brings us to the double negative property. So you hear that a lot, especially in English class. 2 negatives makes a positive. If you say, I can't read, means you can read. So in math, it's the same thing. So if you have the opposite of -a is a, whoops, then if it's a double negative, -a, it will now equal a. And then it gives an example that has nothing to do with this, but we'll continue. So now we want to know, what is the opposite of -3/4? So the opposite of -3/4 would just be 3/4. And then to prove that, okay, I see where this example is going. And to prove that's correct, we can use the double negative theory. Since we learned here that double negative equals the positive, if we do this, Well, then that equals 3/4. So now let's simplify. We have negative, negative 4. So we want to simplify this. I can tell you right off the bat, the answer should be 4. Now let's see how we do this. We want to start with the innermost parentheses by finding the opposite of +4 or +4. So the innermost parentheses, we have -4 now. So we're going to switch this. It's going to reduce down to -4. Because what we're doing is this first. It's inside the parentheses. Now when you have it in parentheses, you need to multiply this by this. And anytime you multiply two odd numbers together, you're always going to get an even number. I know that. So you're basically saying -1 times -4. And what's 1 times 4? That equals 4. So it's -1 times -4. That equals 4. Now we want to do the same thing with negative, negative, -2. Now you're going to start with the innermost. You're going to still have negative, negative. Now, let's start over here real quick. Oops, I already erased that problem. I should have left it up there so I could do backtracking. But so with the last problem we had, where we did -4, that reduced down to this. But now we have an extra negative here. But this part, if you look, is identical. So it's going to be -2, which just breaks down to -2. Now if you see the pattern here, when you had 2, now you're multiplying a positive by a negative. It's going to bring you back to a negative. Oh, here we go. So if there is an even number of consecutive negative signs, then the result is positive. If there's an odd number of consecutive negative signs, the result is negative. Now let's do this one, simplify this one. We have negative, negative, negative 5, and then 1, 2, 3. So first we can break this down. We have -5 now. Now we're going to do this one. It's going to give us a positive because we're doing a negative by a negative. So now we have 5, and then we end up with -5. Now absolute value of a real number is denoted. So the absolute real value of a number, we'll say that's A, is denoted by these two lines. So these are absolute values, and whatever's in the middle. So what this is telling us is the amount of spots it took us to get to there on the number line. So if we're doing 3, 1, 2, 3, the absolute value of 3 is 3. If we're doing -3, 1, 2, 3, it took us 1, 2, 3 jumps to get there. So the absolute value is still 3. which I can actually go into a whole another subset with this. Because think about if we were able to go into the fourth dimension and travel through time, because we could move any direction we wanted to in time. Don't think that you would de-age or stay the same age because you went this way. You went back negative 10 years. You wouldn't be, if you were 30, you wouldn't be going back to being 20. You would still be 30. And if you traveled and if it wasn't instantaneous, but it took you the same amount of time to go negative 10 years as it took you to go forward 10 years, if you started here at 30, well, in 10 years this way, you'd still be 40 because that's your absolute value. You went 10 years. But if you also traveled 10 years this direction in time, you would still be 40 when you got back to where it was when you were 20. Okay, there's tangent. So the absolute value of 4 equals 4. The absolute value of negative 4 equals 4. And to reiterate, the reason for that is one, two, three, four. So to get to 4, it took you 1, 2, 3, 4. 4 moves. To get to negative 4, it took you 1, 2, 3, 4 moves. So absolute values. So if you have the absolute value of negative 12 equals 12, this is a pretty easy concept to get around. The absolute value of 12 is also 12. Same thing. Here's your number line. Here's 0. Here's 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. It took you 2, 4, 6, 8, 10, 12 to get here from the starting point. It took you 2, 4, 6, 8, 10, 12 to get there from the starting point. It's also worth noting that the absolute value of 0 is 0. Okay, this next thing is using the absolute value can be expressed textually using the notation ABS. Okay, this seems like an extra thing I've never seen anybody ever use. We're going to skip over this. Okay, one more little thing for you, for us to look at. So we have the absolute value of x is equal to negative 5. Now, what did we find out earlier? Let's say if we have a negative 10, we want the absolute value of negative 10. It is equal to 10. So how do we have an absolute value that's equals a negative number? We don't. So this is considered undefined. Okay, so what are our key takeaways from all of this? Any real number can be associated with a point on a line. So we can have 1/3. Here's 1. Every number has a spot somewhere on this number line. We created number lines already by first identifying the origin, which is the 0 point, and then making a scale and marking off appropriate for the given problem. So if we're working in tens only, then if we can just go 10, 20, 30. So just -10. As long as everything's consistent, we're good to go. Negative on this side, positive on this side. Smaller, bigger. The opposite of a negative number, so -10, is positive. The opposite of a positive number, in this case 10, is -10. So it's the negative of that number. The absolute value of any real number is always positive because it is defined by the distance from 0, the origin on a number line. And the absolute value of 0 is 0. So, a couple questions we can do here. Let me see where we have the answers at the back. I guess I should have looked for the answers before I did this too. So so I don't see any answers, so hopefully we're doing this right. Anyway, we want to do set notation and list some described events. We'll just do a few. We're not going to do all of them. So if we wanted to list the hours on a clock, we would do 1, 2, 3, 4, 5, 6, so on until we got to 12. The days of the week, we'd write brackets again, and we'd do Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. I guess technically we should have started at Sunday. The next one they want is the first 10 whole numbers. That'd be basically 0 through 9. Brackets, obviously. 0 through 9. The first 5 positive even integers, that'd be 1 through 5. Oh, first five positive even integers. That'd be 2, 4, 6, 8, 10. Comma, 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 comma. Chameleon. Why is that disappearing? First five positive, okay. Now we want to determine whether or not the following real numbers are integers, rational. So 12. Is that a real? Is that an integer, rational, or irrational? Let's go back. So we know that's irrational. So that's rational. It's integer, it's whole, it's a natural. Negative 3 is not irrational. So it's rational. Here we go. This is an example of an irrational number. So we have some true or false questions now. All integers are rational numbers. If we go back to our little chart that we drew, so we had rational, integers. So with this chart, everything above it, so natural is also everything above it, but you're not what's below you. So integers, am I coming out with that correct? So yeah, you're a subset of everything above you, but you don't necessarily include everything below. You don't meet the criteria to be everything that's below you. So whole numbers don't always meet the criteria to be natural numbers because the set of whole numbers is 0 and up positively. So 0, 1, 2, 3, etc. Where natural numbers are all whole numbers except 0. Whole numbers are all integers. So all natural numbers are whole numbers and integers and rational. All whole numbers are integers and rational. All integers are rational. But not all whole numbers are natural. Not all integers are whole numbers are natural. And not all rational numbers. So let's go back to our questions. All integers are rational. That's true. All integers are whole. That's false. All rational numbers are whole numbers. That's false. Some irrational numbers are rational. That's false. Remember, irrational is on the side by itself. All terminating decimal numbers are rational. That's true. All irrational numbers are real. I believe that was true. Okay, now we want to choose an appropriate scale and graph the following set of real numbers on a number line. So here's the number line. So on this one we have negative, so we have the set containing -3, 0, and 3. So we could draw appropriate scale would be by ones. So we would circle here. Ugh, so annoying. We'd circle here, and we'd circle here for the graph. The next one asks us the set of -2, 2, 4, 6, 8, and 10. So here's our number line. Let's see, mostly positive, so we'll put the 0 here. Then we can go by 2s, so that's -2, -4, and then we have 2, 4, 6. So we would graph -2. I'm going to put the circles down here even though they're supposed to be right on the line. So each space is equal to 2, so we're graphing 2. 4 needs to be graphed. 6. 8. And 10. Yeah, the rest of these are pretty self-explanatory. If you need more help on these, I mean, it's just a lot of busy work. So here we want to fill in with a less than, greater than, or equal to. So we have -7 is what to 0? It's going to be less than 30 and 2. So 30 would be greater than 10 and -10. 10 would be greater than -150 and -75. -75 is greater than. And here we have 0 is to 0. That would be equal. -10 and -10. That would also be equal to. So true or false? 5 is not equal to 7. That is true. 4 equals 5. That's false. I mean, that's pretty self-explanatory. List 3 integers less than -5. -6, -7, -8. List 3 integers greater than -10. -5, 0, 5, and 10. List 3 rational numbers less than, yeah, this is okay. So we want to simplify. We got negative, negative 9. Remember, so therefore, that would equal 9. Here we have what does this equal? Remember, this is positive, so now we have negative 1, which equals negative 1. Excuse me. I tried to mute and I couldn't find the button. Sorry about that. What is the opposite of negative 12? That would be 12. What is the opposite of x? That would be negative x. What is the opposite of negative 0.01? That would be 0.01. Is the opposite of negative 12 smaller or larger than negative 11? So we know the opposite of negative 12 is 12. And is 12 larger or smaller than negative 11? It's larger. Because look at the number line. Here's 0. 12 would be this way. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. Negative 11 would be right there in the middle. Here's 12. Remember, this way is smaller. This way is bigger. Is the opposite of 7 smaller or larger than negative 6? So the opposite of 7 would be negative 7. And is it smaller or larger than negative 6? Well, let's see. 2, 4, 6, that would be negative 6. Negative 7 would be right there. So that means negative 7 is smaller. I think. So we got some absolute values here. Let's just do a couple of those. Absolute value of 20. This is pretty basic stuff, though. It's 20. Opposite value of negative x would be x. Opposite value of negative 33 would be 33. Negative, or the opposite value of 0.65 would be 0.65. Simple stuff. Now here's one earlier that we didn't go over. I think I might accidentally skipped it, but it was find the opposite. So this is the question we had. So let's go through this real quick here, because I just saw these questions in the back. So what if you had something like this? So it's asking you to find, these are brackets. Let me redraw this so it's better. So negative So we want to find the absolute value of this. So first find the opposite of negative 7. Remember, that's the middle part is asking you this. So we know that's inside part is going to be 7. So that's going to reduce down to and that's going to equal negative 7. Because remember, what's in here? The absolute value, which is 7, and then that's a negative. We can replace this with any number. It could be 8. And then we just switch this to 8. So in the problems it's giving us, so we have negative absolute value of negative 70. So we know that's going to equal negative 70. Whoops. Pretty simple stuff. Here we go. So what is the absolute value of 15? So x can equal negative 15 or 15. We don't have any more information on that. So then we have this. Well, the absolute value of 0 is 0, so x is equal to 0. Oh, the answers are right after. All right, I think that's where we're going to wrap it up for today. That was 1.1. The next one is 1.2, adding and subtracting integers. That should go pretty quick. I think we all know how to do that. And hopefully it won't take an hour and a half to do because I'll have this thing figured out a little bit more. I think as I get going, I'll go faster as far as the technical side of things go. Things might take longer because of what we're learning. Anyway, that's it. See you guys later. Bye.